Hello and welcome to Team M's VCM production plant Aspen Guide. The process is made up of 7 major units. We have chosen the NRTL to be our base thermodynamic model as UNIFAC is still under development. The following thermodynamic models are considered for the simulation of the reactors. BWR-LS and BWR-S model is not suitable for our process because the process contains significant amount of heavy impurities. The LK-PLOC model is not recommended because it does not consider fugacity coefficients. We have chosen PR-BM model as it is suitable for non-polar and mildly polar mixtures. The stoichiometric reactor is the most suitable model because we have the required input, which are the conversions of the reaction and one or more of the feed streams being identified. The thermodynamic model being selected for the distillation columns is NRTL model based on the same justification as mentioned earlier. DSTWU is chosen because we have all the required inputs while more inputs are required for the RADFRAC model to achieve the similar results. Due to the limitation in Aspen environment, we do not have models available for the scrubber and the quenching tower, hence we simulate the quenching tower by using a heater model. We implemented a stoichiometric reactor as a scrubber. For direct chlorination, the feeds are then mixed and preheated in a heat exchanger to produce a vapor feed at direct chlorination operating conditions of 2 bar and 120 degrees Celsius, and a selectivity of ethylene to EDC at 99.7% is achieved. For oxychlorination, the reactor is a fluidized bed reactor using heterogeneous catalyst copper 2 chloride in the solid phase and a selectivity of ethylene to EDC at 99.7% is achieved. The quenched EDC is sent to a caustic scrubber operating at 30 degrees Celsius wherein liquid sodium hydroxide is fed to remove all unreacted HCl, preventing formation of corrosive hydrochloric acid. Flash drum. Flashing the EDC process stream at 55 degrees produces an overhead EDC stream rich in light impurities and a bottoms EDC stream rich in heavy impurities to distillation column 1, which operates with a differential pressure of 1 bar. Liquid tops is pure in EDC and the heavy impurities are removed as bottoms and combined with heavy impurities from distillation column 2 for removal. For EDC pyrolysis, conversion of EDC to VCM is maintained at 54%, yielding a high selectivity of EDC to VCM at 100%, importantly restricting impurity production, which reduces coke formation. For VCM purification, distillation column 3 operating at 4 bar and 5 degrees Celsius. HCl vapor is removed overhead and recycled for oxychlorination. Bottom product enters distillation column 4 operating at 48 degrees Celsius and 4 bar. Bottoms product enters distillation column 5. EDC is removed overhead and recycled for purification and cracking. As for the energy analysis section, all data would be collected from the Aspen tool. Only 2 reactors generate the energy as they are exothermic and all other units consume energy. The top 2 energy consumption units are the cooler and the heater placed after and before the thermal cracking and reactor respectively. The energy generated from the reactor would be used by heating the cold water to stream and using the stream to heat up the other streams, and it won't be calculated in the pinch analysis. Then the cascaded heat is calculated and the pinch temperature is 230 degrees Celsius to 222 degrees Celsius. After that, the pinch analysis is carried out for the heat exchanger design. It is clear to see 1 heat exchanger is used above the pinch and 6 heat exchangers are added below the pinch with the power labeled beside. However, after considering the cost and the energy saving, we decided not to use the heat exchangers H5 to C3, since the energy transfer is too small, which is not realistic. The heat exchangers are implemented into Aspen and are circled with the green color. The hot stream from the thermal cracking reactor would heat up the other stream by passing the heat exchanger 6, 1, 2, 3, and 4. Furthermore, the mixture of outlets of the direct chlorination reactor and the oxychlorination reactor is used to heat the inlet stream to the thermal cracking reactor. By implementing the heat integration, the energy saved is 75.55 megawatts, which counts for 27.34% of the total energy. I think it's safe to say that you are now an Aspen Pro. Thank you for watching.